All right. Good morning, everybody. Hello. How are you guys
Morning.
today?
Very good, Lieutenant O'Hara. Oh, sorry.
You guys don't know, I am Lieutenant O'Hara from the Space Force.
Very, very good. Yep. So yeah, those of you out there that recognize that, that we will
I'll
have
save
a
autographs
sequel.
for later. All right,
So,
awesome. I see people joining in. You guys are in the right place. This is the AtomBeam webinar. I see some participants hopping in, so I'll give it maybe another minute or so, and then we can go ahead and get started. But just for a show of hands out there, I see a good amount of people are hopping in. If you guys want to try out the chat and tell us where you're tuning in from, it's always fun.
yep, somebody raised hand there.
Somebody raised a hand.
Yep.
Somebody's from San Antonio.
Oh, there we go.
Sacramento. Hey.
All right.
Denver,
Charlotte. Yeah. Boom, boom, boom.
California, yes.
Tennessee, San Diego, Puerto Rico, Greenwich, Pennsylvania. Yeah, there's a lot. That's cool.
God, I love it. I love to see it. Cool. Well,
Bring
thank
it
you,
along here.
everybody. Yeah, we still going. Okay, slow San Luis Obispo. Love it out there. Cool. All right. Well, I think I'm going to hop into it. I know people are still letting us know where they're from and love to see it. But first of all, I just want to welcome everybody. This is our first webinar since the conclusion of AtomBeam Start Engine Raise. My name is Jeanette Cornish. I'm with Digital Niche Agency, and I'm happy to be your host for today's event. So joining me, of course, is AtomBeam CEO Charles Yeomans, and we also have Dr. Zhu Li, who is one of the leading image compression experts in the world. So on today's webinar, we're going to dive into our exciting results and insights from our recently concluded crowdfunding campaign on Start Engine, where we raised over $3 million. And then we have Dr. Li here, who will tell us about our latest product, Neurocompaction. At the end, we'll hold a section for Q&A to answer any of those burning questions. So yeah, without further ado, Charles, I'll pass it to you.
Great. Thanks. Thanks, Jeanette / Dr. Lieutenant O'Hara. So yeah, and feel free to enter in questions too in the Q&A, because as we go, because I'll stop or we'll stop here and there and ask ask Jeanette to give us any anything she sees as germane to the point we were just making. Some of them will hold to the end and so forth. So anyway, so great to see everybody. And I'm really, really appreciative, is the first thing I want to say, for all the investments that have come in here. We're amazed and really pleased at the results of this last raise. They were tremendous. And more than that, or just as important, I think, is the fact that it puts us into a position where we can really power this up. We can get out there, start to really do things. That, in combination with the fact that we have these two phase twos that I think everybody knows about here. Each one was $1.2 million. There is a ton of really, really interesting opportunities for us, and now we can actually take advantage of them. I'm going to be introducing Dr. Li, but why don't you just give yourself a quick intro so that you say hello and all that, please.
Hey, hello everyone. Zhu Li. Actually, my home base is in University of Missouri, Kansas City. I'm a professor there of electrical and computer engineering. But for the last 6 years, I spent my summer as a visiting professor at the Air Force Academy. So my background is actually Mount Shavado. From Mount Shavado, I hiked last year. So my main area of research is image processing, computer vision, remote sensing, as well as compression, which is kind of my forte. So on the civilian side, we have been working with Qualcomm for years in the latest kind of immersive media. Basically, how do you enable metaverse? So all those toolbox, can be adopted for a lot of DoD use cases, for which we will dive into more details today and show what are the possibilities with all those latest AI-enabled tools. So I'll hand back to Charles.
Okay, thanks.
Okay. Mhm.
Thanks, Sue. Appreciate that. Okay, so without further ado, I'm going to spin up our deck here and just start plowing through it. Jeanette, feel free to stop, say, hey, let me ask, here's a question or whatever. All right.
Will do.
All right. Oops, this is sort of in the middle. All right. Okay. So today we're going to be addressing a few things. First, going to make a quick overview. Here's where we started. Here's where we are now. Kind of just a recap. And then we're also going to talk a little about what the plan is to really hammer on this thing and get us to some place where we can say, okay, one way or another, whether we do it or not, we'll be in a position to sell this if we want, or somehow get liquidity, IPO, whatever, in a reasonable time frame. But now we have some resources, so now we can make those commitments and make that move forward. And then, of course, we're going to talk about neurocompaction, which is the sensor image focused version of compaction. Lot different than standard compaction. We'll talk about what that is and why and all that. But just quickly on the recap. So when we started, we had 11 patents. We now have 20. Well, we had 29 at the close, and now we're accumulating still more of them already. We didn't have any contracts with DoD. Now we finished one, and we're about to finish a second phase one. And of course, we have these 2 phase 2s, each of which is $1.2 million. A key point is we really need high-level engagement with AWS and Azure. Those are cloud services, and that is how the most important part of going our go-to-market. So when we say, okay, when somebody says, hey, I'd like to use your stuff, how do I do it? Go to AWS, push this button, and it's now in your stuff and working, and all you're doing is paying for it. That's the goal. Now, it's not quick, not easy, but engaging with those two big cloud service providers is the key thing that we needed to do. And now we're doing it. We didn't have very many partnerships when we started. We now have a pile, as you can see, and there's more coming. We really didn't have enough money to really make plans or push things forward. We've raised 3 million plus. And we only had one product. And now we have compaction, but we also have neurocompaction, which still needs to be worked, needs more work to become an actual product in the sense that somebody can buy it and pay us for it and use it and all that. But we are definitely, I can say with a lot of confidence, this will be a product that we're going to be able to sell. And just thinking about what the strategic difference is between where we started and where we are now. Where we started, we talked mainly about IoT, right? Basically speeding it up, expanding bandwidth, and adding security. That's mainly it. But now we're really able to talk about things that, part of it was putting out, being able to talk about searchable data at rest and being able to basically change how all the data that's used out there can be so much more efficient. That's a thing that we've really advanced ourselves on, and it expands the opportunities for AtomBeam like exponentially. And so we'll move on. Let me talk about the plan, and feel free to interrupt me, Jeanette, if you like. But basically, what we're really doing right now is we're formulating an 18-month plan. And the 18 months, we're going to be focused on trying to get to a point where we can say, okay, we've got 2 products. They're both solid. They're both used in the market. They both have all the productization, that is to say, all the ease of use, automation, and all that need to be in place. And we're going to target being at that point in 18 months. And that implies a bunch of people, clearly some heavies in terms of bringing in engineering and really strong senior people, more experienced salespeople, and getting ourselves in a place where we're really able to support our customers and our partners, sales engineering and things like that. And it's really coming down to this: what can we do to our products to make them really simple, easy to use, so that, again, somebody just says, hey, this looks good, I'd like to use it. Here you go. Push this button, pay us, and you're off to the races, you're using it. That's the goal. And if we can get to that, then guess what? All these guys will be using it. We'll be installing it in the cloud. And as I think a lot of from earlier things, ideally they already have a chip in their device, and the device can connect automatically to a cloud that's also provisioned with AtomBeam compaction, and if appropriate, Neurocompaction. And so now these things can just automatically connect because you already have it on both ends. So this is where we're going. And the focus right now internally, we're continuing to work on the product and all that stuff. But the key thing is we want to have this really in-depth plan and what people we need and all that stuff. And that's the focus right now. So again, focus to get to in 18 months, we're looking at a really, really heavy duty opportunity. And so what do we need to do that? Well, I think everybody knows that, you need money. And part of what we've got about 2 million in the bank right now, because some of the money we raised, we spent on engineering and all that. And then, but it's enough right now that we can really put the pedal to the metal. We're going to need more. There's no doubt about it. But we've got that, and we have these contracts that are going to pull in some, that already have pulled in some money, but they're going to be pulling in more the rest of this year. And then we are going to be going out and raising more money. It's possible that we go raise more crowdfunding. I wouldn't have said that before, but I think there's such a strong understanding and appetite for what we're doing. And I think there's a lot of excitement out there, and I think it's justified that, we're going to look at possibly doing more crowdfunding, because I like it. I like, I'm a Stanford MBA, and my fancy pants friends, are big time venture guys and billionaires and everything. I like it that, it isn't just limited to, okay, I'm a Harvard MBA. Oh, okay, well, that's good enough. My point is, I really liked the idea of crowdfunding. I like the idea of it not limiting ourselves to just institutions. Now, that's not to say that we don't end up going to get institutional capital. I'm not saying that, but frankly, if we can stay away from VCs, I'm happier. I'd like to take in money from a partner like Viasat, but we're going to have to see. But at the same time, I'm not saying absolutely, but I am saying it's definitely something we're considering. So. Okay. All right. So let's talk about the star of the show. And that's neurocompaction. So, and really, we're going to talk in general terms about some of the things that apply to any image compression. But what neurocompaction is focused on, and this is the thing that Dr. Lee's magic really does, is it addresses the particular problems that you run into when you're trying to reduce the size of images that were by sensors, and especially certain kinds of sensors. And so we're going to be talking about that, here, and that's going to be the main topic, simply because this area is growing hugely. Autonomous cars, other than Tesla, use LiDAR, pretty much. LiDAR and synthetic aperture radar and hyperspectral images and all kinds of other sort of images that are generated by sensors, including electro-optical, which means cameras and stuff. Those things are all produce giant images, and they need to move those images from here to there. And that's where we come in. So we're going to be talking about this. So, Dr. Lee, you can jump in here if you like.
Sure. Yeah, so Charles is right on the point. I mean, especially for the DoD use cases, like the latest Ukraine war demonstrated. Actually, competition is more or less on the information gathering and processing capabilities. So actually, the sensor side actually made a huge advance. So all sorts of sensors are just getting better, cheaper, and can be deployed anywhere on any platform, right? From vehicles, UAVs, airplanes, satellites. So, but all this information are useless. You cannot derive any tactical value unless you aggregate those information. So, but the sort of the radio spectrum is limited, right? I mean, it's being saturated with different applications, devices. So it's really critical to be able to compress those sensor informations and send them back to either edge or the center for some processing. So this is where kind of this compression comes in for this DoD use case. So surprisingly, I mean, actually the civilian side, I mean, this is a very well established field. So like 20 years ago, I did my PhD at Northwestern in Chicago. That was the time of the dawn of wireless video. That was right before 3G takeoff, right? So one of the main killer application people were envisioning is like a wireless video, make it available everywhere. And now it's becoming a reality, right? You pull out your cell phone, you can watch HD kind of YouTube videos. That was unimaginable like 20 years ago. It was a big technical challenge. So it's kind of fortunate for me, I got a training at the time in this compression kind of a topic. So after PhD from Northwestern, I actually spent like 8 years with Motorola Research in Chicago. I mean, we are one of the leading sort of research group in the world in the video compression before the AI age. So back then it's many signal processing and optimization techniques to make it working. You wouldn't imagine how many lines of code kind of, because these days people take for granted, right? You pull out your phone, you can watch YouTube video. But what's behind that is like millions of lines of code. So anyway, so in a way, I'm a veteran in this area. So compression is the bread and butter of my research. And ever since joining kind of University of Missouri, like 6-7 years ago, from Samsung. I mean, back then I was working for the Samsung's compression team in Dallas. So I saw some people actually from Dallas. So anyway, so ever since joining that, I was I'm not only doing the compression, I'm also kind of we got the FOSR project funded. And like the second year, I joined the UMKC, and it was a joint project with the Maryland side. So we've been working with FRL in like hyperspectral imaging, in NIDA, in point cloud kind of a topic. So this year, I'm very happy. Actually, we won a grand challenge at CVPR in Vancouver just last month. So in Vancouver, they have this kind of grand challenge on PBVS, perception beyond visual spectrum. So that's I mean, the whole grand challenge was actually organized by the Air Force Research Lab in Dayton, the Sensor Directorate. So it was very embarrassing. For 3 years, they ran this grand challenge. I mean, non-US team has ever made into top 10. So we are the only US team actually made into top 10 last year. and then one of the winner, one of the top 3 winners this year. So it was pretty significant. So if you look at actually the problem itself, it's a very challenging problem. So they basically have those satellite imagery of the ground through the electro-optical sensor, which is passive, as well as from synthetic aperture radar images, right? So through those 2 images, I mean, they have those 2 challenges. So one is the SAR image only, the other is like a SAR plus EO. So in both categories, we made into top 3. Actually, we are actually number 2 in track 1. So anyway, the Air Force lab was very, very pleased. So it was quite embarrassing because like this year, the top 10, right? 8 from China, 1 from Korea. We are the only US team made into top 3. So in a way, my lab has quite a bit of credibility with the Air Force on the sort of computer vision remote sensing side. So speaking of hyperspectral imaging, we are also one of the best team in spectrum super resolution. So we all understand like hyperspectral image, right? They have a much higher spectrum resolution, which can lead to many useful military kind of values like detect camouflage, this and that, but its spatial resolution is very limited. So it's very natural to combine like a regular EO sensor, right, which has higher spatial resolution with hyperspectral image, which has higher spectrum resolution together into a more powerful sensor. And again, through our previous FOSR project, we are the best in the world in the spectrum super resolution. So we take a RGB image and we use AI to recover spectral information out of it. So this project was very successful.
Steal your own thunder here, Zoe.
Yeah, that was really very impressive. So the Air Force side was very very happy with that.
The thing to emphasize here is that Zoo's team is the top team in the United States and one of the very top in the world for what we're talking about doing here. This is, I mean, you're literally looking at like the top guy in the United States and one of the 2 or 3 top guys in the world for this particular application. And so, I mean, you know, I got to tell you, we were really, really lucky to get an opportunity to work with them. And that's why, and it isn't just me saying it or even Dr. Lee saying it. This is the Air Force Research Lab are the ones who sponsor these competitions. And this competition is the most competitive, the biggest and the most widely recognized competition of its kind. I believe that's right.
Yes, right on the point. So anyway, so moving on, a little bit more detail. Can you go to the next page?
Yeah.
Please. Yeah. So at this time, I mean, on the compression side, right? Our lab is looking at several kind of modalities. So roughly speaking, right? We have those like a regularly sampled images versus irregularly sampled. So like hyperspectral image, EO images, SAR images, those are images which is sampled on a uniform grid. So this the implication of this is you have a set of signal processing and AI tools where you can use. But on the other hand, I mean, for the LiDAR, right? For the LiDAR kind of type of sensor, when you have those point cloud kind of imageries, I mean, those images are not regularly sampled. So all those existing kind of tools is not working. So for this purpose, actually, we are one of the first in the world, I mean, in this point cloud compression research. I was an ad hoc chair at MPEG since 2016. That was when it's launched. So for LiDAR type kind of data compression, we developed a totally different set of tools to deal with that. And again, in both fields, we are one of the best team in the world on that. So, okay, Next page, please. Yeah, so talk about the sensors, right? I mean, sensor is probably one of the most important kind of differentiator in the effectiveness of military in the world these days. I think, I mean, hardware-wise, I mean, like cannons and bombs, they are more or less the same ever since World War II, right? But what really made the difference is the sensors and the information processing, aggregation, communication, processing capabilities to that. So roughly speaking, I mean, the sensors we are dealing with are like active sensors versus passive sensors. So most of the compression technology developed before for commercial use was for like a passive sensor, like a regular RGB camera. So all those tools, in a way, they exploit the statistics of those pixels, right? They're happening in the spatial temporal domain in a particular way. So directly just utilizing those tools may not work in the use case we are dealing today, like for DoD, right? So like an active sensor, I mean, like a SAR, for example, right? You shoot a EM wave and you measure the return signal as a complex signal representation. I mean, they have totally different kind of characteristics. So to have effective compression, we need to develop new tools. And for the passive kind of sensor size wise, right, like those EO imageries and hyperspectral images, I think the main problem is, I mean, the volume of the data is huge. This is unbelievably huge. So imagine, right, you deploy all those sensors, you need to process those information, aggregate them together to derive some technical values, right? So compression is essential to that.
Essential, right?
Yeah,
No,
yeah.
You know, and just to emphasize here, the difference is, you know, like active is just when you're sending out something and you're measuring how long it takes to come back to whatever it is the sensor is that you have, and the and passive, all you're doing is taking whatever is there, and, you know, and then measuring that. So, you know, I mean, and you're in the technology of neurocompaction applies to both, right? I mean, it's essentially just a way of taking an image generated by a sensor, and the sensor could be optical, not to deny that, but the biggest problem that the world has right now, and especially the military, is how do you deal with the images that were created by non-optical sensors, either passive or active?
Yes, like a long traditional kind of imagery we get used to, right? Like your
Exactly.
Instagram imagery. So
Yeah, right.
Very interesting side note is like a U.S. Air Force started as a signal corps under the Army, right? Because I mean, like 100
right.
years ago, they only see kind of airplane as a usage as a sensor, right? Because I mean, 100 years ago, right, the sensor is like a human eyes flying an airplane, and then the communication link is just a radio link. You have voice communicate back, right? Oh, there's a company of cavalry kind of charging at you, something like that.
Right.
But now it's like 1,000 times more advanced sensors, and all this information, right, not possible to communicate over a voice channel anymore. So that's kind of a very interesting kind of technology kind of revolution going on.
Yeah, right.
Yeah.
No, that was a really interesting point you made.
Mhm.
Like, okay, bombs are bombs. It's a question of where you put them.
Yeah.
You know, that's the difference. How accurate can you be about where they're going? So just to, you want me to do this, start this one out?
Yes, it's next slide, right? So okay, so yeah, my screen just locked up. Sorry about that.
Oh, okay.
Yeah.
Well, I'll
Yeah.
start talking about it.
So
Oh, go ahead.
okay, so for this particular Air Force project phase 2, I mean, we are focusing on the SAR imageries. So like a synthetic aperture radar has been, I think, been around for like 30 or 40 years. I think the main advantage of this over those passive sensor is it's weather agnostic, right? So it's rain, hazy, or foggy, right? I mean, your passive sensor won't be able to see anything, but with synthetic aperture radar, right, you can still see them. And on top of that, I mean, because it's an active sensor, I mean, they have a very unique applications in those like a change detection. So actually, in the recent war, actually, those change detection is a big deal. So when you sort of try to figure out what are the enemy's move, right? I mean, those change detection actually kind of at a massive scale actually give you very strong evidences to make a judgment. So this synthetic aperture radar in a way is very high resolution, because imagine you put them in on a satellite or on an airplane flying around. I mean, they scan the ground and they generate a huge amount of data. So to make this information useful, right? I mean, we need a compression. Otherwise, kind of it stays with the airplane, right? So back at the headquarters, I mean, you don't have this information, then it becomes useless.
Yeah, and you know, so basically, just to go back on, you know, this is really basic for Dr. Lee, but I got to say it just so everybody here is like, I got the same background. Basically, you get a lot higher resolution from a radar return. You can create an image out of it, if you have a really big antenna. And the problem is you need an antenna like if it's in a satellite that's like 100+ miles wide. And so how do you do that? Well, the way you do it is you fake it, you synthetically create it. And you do that by, as the satellite is flying over the object, then it's pinging it with radar waves and getting a return. And it does that over and over. And so that in effect, you have this really big antenna that's received really multiple images that are put together as one, which is how you really end up with these higher resolution things. And as Zhu was saying, it's all weather. It's a key point that it doesn't need to be, you don't need to if you have an optical satellite and you want to look at a something on the ground, and it happens to be, overcast that day, well, you're done. Whereas radar, boom, goes right through it. And so that's one of the reasons why DoD is so focused on it. They're not dependent on weather.
Yes.
So
Yeah.
Any other points before we move?
Yes, please go to the next page.
Okay. So
As
I
for-
dropped out the slide a little bit, so just don't be surprised. So
Yeah, and then the LiDAR in a way is similar in principle, like for synthetic aperture radar. It's just instead of shooting a EM wave, right? They are shooting a LiDAR beam. So this way, when you measure the bounce back, right, you can have depth information, basically geometry information of the sceneries you look at. So on the commercial side, actually, for auto driving, this is one of the key sensors to enable auto driving. It's like maybe 5-8 years ago. I mean, those LiDAR sensors for auto driving is still expensive. But nowadays, I mean, the cost has been dramatically kind of driven down. I mean, it used to be like $10,000 or something. Now it's like several $100. You can have a 64.9 kind of scanning LiDAR sensors. So you would imagine, right? This also has a huge potential for military applications, like autonomous kind of fighting vehicles, right? How do you navigate them, run them around? So actually, in fact, 2 years back, we were trying to get a project on this front, like how do you automatically landing a rotary machine or fixed wing asset onto a field, right? Giving you have a point cloud which generated from LiDAR. So all this also involve a different modality. So basically depth geometry information, irregularly sampled. How do you communicate those information, right? For a variety of applications is still kind of, I mean, is also one of the topics we are very interested in. So next
yeah,
one.
and one point I think it's important to make on this particular slide is this atmospheric scattering. Because that is one of the things that makes these kinds of images really hard to compress, because it's adding in a bunch of noise, that random stuff that, if you were doing this through a vacuum, you wouldn't have to deal with. But, the atmosphere, makes things bounce all over the place. And so you've got to account for that. And that's one of the things that Dr. Lee's AI does. Dr. Lee, why are we in the LiDAR image on the right? Why are things red or blue or anything? Is that just colorized or what?
I mean, it's just they just give them a pseudo color to indicate the distance, or maybe the reflectance. So they have different reflectance values.
Okay.
So somehow related to the material.
So yeah, so you're going to have less reflection, say, on grass than you would on a piece of concrete, right? Okay.
Yes.
All right. So do you want to talk about this one?
Yes, I jump first. So hyperstructure is actually the topic we first worked on for the Air Force. So like I mentioned before, right? I mean, the main advantage of hyperstructure imaging is they have a very rich, fine granular spectrum information. So actually, through the Air Force project, we actually get another project on National Endowment for Humanity, studying those scriptures from different churches, like 500 years ago. So it has very wide application, and the technology is well developed, and the products are anywhere. I mean, everywhere for civilian use, for military use. So one main challenge for this is a huge amount of data, right? We are talking about the hundreds of channels. So regular imageries, right? You have RGB 3 channels. But for hyperspectral images, we typically look at maybe 100 to 300 different channels, kind of sampling your spectrum. So this rich information can lead to many useful applications. And but to make them useful again, we need to compress them so they can be communicated.
Massively. Right.
Yes.
How big are these images typically?
Yeah, so typically say spatial resolution is 1 megapixel, right? So if you have 3 channels, it's three megabytes without compression. But if you have like a 200 channel, right? It's like a 200 mega, right? Without compression. So that's a huge amount of information.
Yep.
And if you add a temporal dimension to that, right? That's even more massive, right? So you take a hyperspectral video, say 30 frames per second. So you can imagine the amount of data generated. But indeed, actually, all those pixels, right? They are very much related to each other. They are not happening in random. So that's where this AI and signal processing schemes will exploit these correlations and be able to represent them in a very tight way.
Right. And so the key thing to understand about this is, you know, instead of like just saying, okay, it's either red, green, blue for this pixel, it's a whole big range of possibilities. You know, like with Macintosh, they'll talk about millions of colors, right? And so you're talking about a really, really deep thing, lots of things that it could be within this range, not just it's red or it's green. So those things means in effect that you can use that capability to identify what a material is. So you can say, aha, this place over here is got some pollution, or this place over this cornfield has weeds in it, or whatever. You can do all sorts of things to detect what a material is. Or it's when they use spectrum analysis of stars to say here's what they're made of. So there's all sorts of uses for this thing, but you know, the size of the images, as Zoo keeps mentioning, is really big and a big problem if you're going to do anything other than use it in a fixed location. Yeah,
so one of the main use of hyperspectral imaging is to defeat camouflage, right? So say if you deploy a brigades somewhere, you hide them, right? I mean, hyperspectral, because material, hyperspectral signatures represent different materials. And also over time, right? Over time, all those changes. That's exactly what they use to kind of figure out what the enemies are doing. So it's like the early days, right? When you observe with human eyes, right? Like you have a reconnaissance kind of aircraft and this and that. It's just leap and bounds difference.
Yeah.
Not easy. The whole modern battlefield is totally transparent. It's very difficult to hide anything because of this sensor technology. So how do you aggregate this information and process this information in time to give them tactical advantage, right? That's where the key computation is.
Point. Yes.
Yeah.
And then again, you've got to move that data from whatever's taking the picture to wherever it's going. And I got to tell you, one of the things that is really big is to be able to do the analysis on some place on the ground, some central point on the ground, after the image has been sent there. And so how do you get the image there becomes a big problem. And as Dr. Lee is saying, the amount of bandwidth you can use is really, really constrained. So at any rate, so you can see all these, the point is on these, so these are 3 kinds of images. There's a lot more, but these are the things that are sort of like screaming for some way of reducing them more effectively than the state of the art does. And that's why we're emphasizing it, that and the fact that neurocompaction is, the answer, which is why the Air Force Research Lab gave us this grant this contract, and we're able to really, focus a lot of attention on this stuff because they see this as a critical thing. It's great if you can take all these images in your satellite, in your aircraft or whatever, but you can't do much with it if you can't send it somewhere. And so this really goes to kind of like the things we were just talking about, which is
Mm.
what can you actually do with these things, or what are they used for? And it's like, you have no idea how much this is going on. You may be being pinged right now with SAR, with LiDAR, all that kind of stuff, and you have no idea, because it's everywhere all the time. And it applies to, to not only military, but just, LiDAR, I got to tell you, that is growing like crazy. And there's some pretty big companies working on it. The complaint that Elon Musk has is that LiDAR can't get through heavy fog and rain and stuff. But the LiDAR companies say they've solved that both through the wavelength they're using and so forth. So they probably have to a large extent. But at any rate, LiDAR is really what you see in most autonomous vehicles.
Yeah, on top of that, actually, we also work with a company in Kansas City. I mean, actually in Lawrence. So they use millimeter wave radar for this. So actually the group they used to have a huge project kind of doing like a land penetrating kind of imaging for the South Pole kind of ice study. But this technology has made a huge advance. So the combination of LiDAR and millimeter wave radar can give you a very accurate picture of geometry.
Yeah, I mean, it's a good point. You don't necessarily have to just use one of these things. You can merge images, you can use multiple approaches, and then you, of course, there's all the things that you can do with machine vision. That is to say, figuring out what it is and whether it's something it's important or not. So, this brings us to really neurocompaction itself and what it is why you need it. And it comes down to this, that the state of the art of compression for image compression, it can't really solve the key problems that you run into with these kinds of images. And so the effectiveness, it's effective, but it isn't nearly as effective as it is in the context of the approach that neurocompaction uses. Feel free to jump in here.
Sure. Yeah, so neurocompaction in a way compare with the previous handcrafted solution, right? So for different modality, different imageries, they just handcraft signal processing, signal representation kind of solutions. The neurocompaction kind of allows this to be self-adaptive. So we train the compression pipeline with a neural network. So instead of we kind of human kind of optimizing them by hand, we need a system end-to-end to optimize that. So this leads to huge advantages in compression efficiency. And another point I will try to make is all this, right? I mean, calls for standardization-based approach. So on the commercial side, right? I mean, all those image format, I mean, it's agreed upon standard. So this is standard-based research and sort of development enables interoperability. So this would be a very good point that we can make to the higher up, say, I mean, for both, for the military. So basically across three services, they need a unified kind of standard for all sorts of imagery compression, and then somehow kind of become a standard as part of, say, AR16 or AR22, whatever. So we see there's a huge opportunities along this trajectory. Not only we develop a compression tool, but we also define a standard which enable interoperability.
Right. No, it's a really good point, because like one of the things you find is, just so everybody gets a little more background on what Sue was talking about, Link 16, Link 22. So right now, most of the US military sends most of its information between different platforms, airships, ground, whatever, over something called Link 16. Now, I've talked about this in another webinar, but in the quick review, Link 16 is a 1980s technology, and the speed of the data connections, it varies. It's either 23, I think, 57 and 111 kilobytes per second, not megabytes. and certainly not gigabytes. And so
Mhm.
it's the speed of dial-up from You've Got Mail era. And, you know, it is what it is. That's what they have. And they're all working like crazy. The DoD is working like crazy to come up with new, highly survivable, error tolerant links. But for the most part, that's what it is. And that is what it's going to be for a long time, because the allies of the United States are probably going to be very slow to upgrade their systems, even if the US did theirs. So you got to deal with what you got. And if you're trying to send a 200 megabyte image, a lot of them over a 56 kilobyte, 57 kilobyte connection, you know, you're going to be at it for a while. I mean, and it's going to clog everything up. So what do? You got to cram it down as much as you can, because you got that, you've got the satellite links that are, you know, very limited. You have all sorts of RF, you know, the radio connections that are really, really limited. And so this is a big problem. The Air Force has a whole set of people, a whole, you know, dedicated group of people they call the ARDUS program, dedicated to trying to deal with this problem. And those are the guys that we're engaged with on neurocompaction. It's you know, it's something that is absolutely a huge priority. And one of the cool things is, if we are successful here, and and I'm confident we will be, but you know, if we're successful, this can move into phase 3. And it could even move to multiple phase 3s. And phase 3s are cool because they're $15 to $20 million each. So, and that would be moving to deploying it into, you know, actual like fighters and satellites and you name it. So, moving right along. So really quickly, this is just a quick overview of what neurocompaction is and what it does. So basically, you start out with an image. And in the neurocompaction combines AI with a codec, and Dr. Lee will explain that, and he'll say, okay, is this an image? Yes. So put it through the full boat, you know, the AI, the codec compaction, and send it over here. If it isn't, then it will move it straight into compaction. That is to say, if it's telemetry or something, and in standard compaction will compact it. But a key thing to understand about any image compression and compaction, neurocompaction, is that with compaction, compaction is lossless. You don't want to know approximately the location of something. You want to know exactly. You can't afford to lose any bits, any information. And so compaction, standard compaction, it always has all the information that was in the original message. So you don't lose any of that. You can't. Neurocompaction, like every other image reduction technology, does eliminate a lot of the data. So it's called a lossy approach to image reduction. And the trick of it is to reproduce on the other end an image that is fully recognizable, it's useful, it has sufficient resolution that, and lack of noise in it, that it can be used for whatever the purpose is. So again, lossless compaction and lossy image compression, or image, in our case, neurocompaction. Just want to emphasize that so that everybody's got it straight. All right. Okay. So you want to talk about this very briefly?
Sure.
I just want to hop in and remind you guys, we have about 10 minutes left.
Oh,
so
okay.
I don't want to cut you off, but
I'm glad you did.
Yeah, so
waiting to jump in.
Thanks. So we'll be quick on this part. This is more technical part. So the current framework we come up for the Air Force is like this combination. So we use a sort of handcrafted codec to come up with approximation of the signal, like the SAR imaging in complex domain. And then we use the AI module, which is totally adaptive to the task to recover information from this approximation. So this way we can sort of achieve very significant compression gains out of it.
Good. All right,
Okay.
so we're going to have to go really quick because
Yes,
I
next
want to
one,
get some
please.
questions in. And by the way, interrupt us with any questions. Feel free. Do you have
Yes.
anything, Jeanette? That
Yeah, I mean, there's a few that have popped up.
Okay.
Let's see. So somebody, okay, she popped it in. We have, or Steven, sorry, I thought it said Stephanie.
Okay.
Okay, you mentioned applications for Earth-centric views. Any thoughts on radar facing out to space, scanning LEO objects? Any discussions with DARPA or related federal agencies for funding? AtomBeam tech sounds like next-gen data burst technology, packets, etc. Correct understanding?
that's one for you. So
So for facing to outer space, I'm not very familiar with that. So probably need more information on exact use case. So but in general, I mean, any data you need to be sort of communicated between two endpoints. We need some compression to conserve bandwidth. I mean, especially for those deep space communication, right? The effective bandwidth is very limited. So
right.
we see a use case here.
Both compaction and neurocompaction that would be applicable for that kind of stuff. Yes.
Yes.
But yeah, that's a really good point. Yeah, somebody like NASA, especially. And you're right, for the deep space network, that's a good point.
Awesome. I have some other ones coming in.
Fire away.
Okay, and I think this was related to one of the slides that we just passed, but do these 200 megabyte images that need to be compacted have to be rebuilt into the exact same image, or can be some loss in creating the original image?
Yeah, I think the next slides answer this question. So if we quickly go to the next slides.
Yep. All right.
Or maybe the next one.
All right.
Yeah, this one answers this question. So it's like of course we can afford some loss of information, but it won't affect its tactical value. So this is like a typical star image, right? So the left side is original, I say 200 megabytes. And this one is like a compressed maybe 100 times, right? 60 megabytes. As you can see, right, reconstructed magnitude image more or less is the same. So basically, this imagery is on a parking lot that's somewhere in Dayton. So you can still make out of those vehicles. So for all technical purposes, I mean, we can afford some compression, but we need to do that in a smart way, so we don't lose useful information and keep noise.
Right. So here it is in numbers. To take, like, for example, you're starting with a 32 bits per pixel image. So each pixel has 32 bits of information that's set to in the original, right? And it's like that's a lot of bits, right? A lot of computer bits, ones and zeros. So what Dr. Lee's stuff does, and that last one was CRF 25, and that's a measure of how good the image is as a reproduction, right? And so is this PSNR thing. It's how much noise is in it. But he takes this 32 bits and turns it into 0.4 bits per pixel. And that's how you get to the 78:1 ratio. Okay, so, you know, and that the other one was slightly different, the next one, but to get to this compaction multiple, you take 32 divided by 0.4097, and that gets you to 78:1. And so think about that. You're taking something that's 78 times more information, and you're getting an image that's pretty much the same. Okay, like that's like holy crap time, right? How can you do that? And it's through using this AI. And I want to emphasize that is not something anybody else does. I mean, we do that. Neurocompaction has this super duper AI, and it's really just a way of eliminating a lot of like the extra noise that's in there, the scattering of information. And it's pretty incredible. And that's why the Air Force is like really, really excited about this stuff. So And that is really what just quickly on what the goal is. As I mentioned before, we're working with a research lab now, but the goal of this is to get to phase 3. And the phase 3 could include all sorts of areas. Now, this is right, the Air Force, that's we know the 2-star general that runs that, it's called C3INN. And down on the lower left, that's the Air Force, I'm sorry, the Space Force's, well, it's called Air Force still, they're messing around with it, but now it's the Space Force Satellite Control Network. And on the right is the Naval Information Warfare Systems Command, run by a 2-star admiral that I know as well. And so all those things are pretty cool. But those are the guys that we're going to be taking what the work we do here in phase 2 and then saying, hey, is this interesting for you? And they're already talking to us and interested. So we just need to push it along more and get more work done and package it up more. That's what we're doing. And not only that, Dr. Lee has a lot of ideas to make it even better. And really, it's like, okay, you combine it with our other stuff and you put it on cloud services and on chips, and now you've got a complete solution that everybody's going to want. And there's lots and lots of places you can go with it. It's enormous, the amount of opportunities here. And I know I'm kind of flying through this, but I want to have a little bit of time for questions. So neurocompaction is a key thing for AtomBeam. Why? Because it gives us 2 products that makes us more substantive, and it also not only that, the Air Force is paying for its development, and you combine it with compaction, and now you've got a really cool combination product that lots of people are going to want. Jeanette, give us a question.
Go. How does AtomBeam's technology relate to, or let's say integrate with, quantum technologies? Sorry, it just popped off. Somebody put in another question.
So I can answer that. I mean, this one has nothing to do with quantum. And the quantum computing has a long way to go. I think in the next 10 years, we won't be able to see any practical application. Still has a long way to go to be practical.
Okay, good. Quick answer.
So I guess this one relates to the last slide, but when are the phase 2 projects to be completed?
Oh, officially, I think it's 21 months, but you can go as fast as you can go and they want to go and all that. Officially, phase 2s, I think, are 21 months, but how quick you go and how, frankly, how quickly you're paid is really dependent on how fast you and your sponsor, that is in this case AFRL, are willing to go. And they're willing to go pretty much as fast as we can go, which is pretty fast.
Awesome. This comes from somebody who invested in 2021. They're saying that then it was called a convertible note. Has it changed to a share?
Yes, you should have, everybody who invested in the first round who got convertible notes converted on January 5th, 2023. If you have not been in receipt of a notice from Start Engine, let me know. You can either send it to me, Charles at info@atombeamtech.com, or send it to info@, or post something in the discussion section of the most recent one. When we'll answer, we'll make sure that that Start Engine reaches out to you, because that's them. There's the ones who are keep that and are responsible. So yes, it converted, and you should have had a notice.
All right, awesome. Who are the primary beneficiaries of the improved sensor images through neurocompaction? How will this technology positively impact their operations and capabilities?
Okay, we kind of addressed that some, but Zoot, if you want to.
Yeah, sure. So like a spectrum is the main limiting factor, right? So like these days, even a company level, you can deploy dozens of different sensors. How do you get those information back, right? So it's not the sensor capability, it's the communication capacity that's limiting how much you can do. So if we can improve compression by say 2 times, right? Imagine, I mean, the tactical advantage you can have over your enemies. So
Massive.
maybe I think the DoD will be very interested in the technology we have.
Yeah, and that's not even to address the commercial opportunities. I
Mhm.
mean, you have to move all that LiDAR stuff around in a car, for example. An autonomous car, has limited capacity in terms of the internal network. You've got to have a lot of data move. And I got to tell you, we are already in discussions with one of the biggest chip makers for cars because they need to move more radar data around in that car.
Cool. I know we're coming up on time. I'm going to ask maybe 2 more questions and then we'll wrap it up from there. This one says, how many engineers have you brought on since the raise ended?
Yeah. The answer is 1 almost, and a very senior guy we're working on right now. But we're in discussion, we're in hiring mode, but part of the thing we have to be sure about is having our ducks in a row in terms of having our plan fully squared away and so forth. Part of what we do, we have people in Bolivia, they can't work on the source code. We're working through to get a plan together, how many people to hire there versus the US. In other words, we're not just charging in and just running out and hiring a bunch of people. We got to have very specific ideas about what their skill set should be, how much we can spend and all that. And it's all, this is a plan that very actively being worked on.
Cool. This one kind of has 2 questions in one. What is the whole NAVWAR designation, and will the Navy use this technology in their support and or logistics?
So NAVWAR is the term the Navy uses for the Naval Information Warfare Systems Command, which is the system command run by Admiral Douglas Small. And it includes basically all the work on the Navy's, among other things, communication systems, as well as intelligence systems and so forth. They're the ones who develop and prepare for deployment the systems that ultimately the warfighter, as they like to say, uses in the field. And so NAVWAR, but NAVWAR also includes like intelligence activities where I used to work, frankly. But it's a fairly new thing, but it includes a lot of different things. It's a very important command in the Navy.
All right, awesome. So we're at 12:33. I know we have tons of other questions still in the chat. I wish we could get to them all, but we'd be here maybe the rest of the afternoon. I'm going to drop in, I know Charles had mentioned it, the previous Start Engine campaign page. You can always go there, drop into the update section, any questions that you might still have. I know
The
Charles,
discussion section, yeah.
discussion section, yeah. So that is still up and running. You can still communicate through there. Also, Charles mentioned his email address. You can email him, sounds like directly. Somebody's asking, is this deck going to be shared? Charles?
I'd be happy to share it. I'll post it up on a link onto the discussion section.
Great.
And you can put it in a link to it in an update, actually.
So we'll have links to it in an update, and that page is still active even though it's not actively raising. Any updates are still happening there. I just want to thank you guys both for hopping on. This was very informative. Feels like we could talk about it all day. But yeah, this is a great overview talking about the newest product, Neurocompaction. So Charles, thank you always. And Professor Lee, thank you so much for joining us. I know that we're probably going to have some other webinars coming up. So you guys stay tuned. Like I said, update section, social media, blogs, all of that. We will definitely make sure to keep you guys updated.
Okay.
Anything else you guys want to say before we wrap up?
No, I just want to thank everybody for coming and spending all the time. And also thanks, Jeanette, and thank you, Dr. Lee, for your very valuable time.
Awesome. Enjoy the rest of your day, you guys. Thank you.
Have a nice weekend.
Thanks very much. Have a nice weekend.